we want to solve this week is as follows. We want to find all triplets x, y, and z consisting of positive integers which satisfy this equation. Before discussing this problem, I want for us to review the order axioms of the real numbers. These are the axioms we use when we need to manipulate inequalities, and I will make use of them a few times while discussing the problem of the week. So the discussion will be easier to follow if we review these axioms first. We can actually solve the problem of the week without formally acknowledging that we're using these order axioms. But using the order axioms actually makes the discussion a little more clear. Additionally, for you to be able to understand the first 5 lines of the written solution to the problem of the week, you'll see that this same collection of order axioms is used to do the introductory case analysis. In this video, I will provide an alternative case analysis, which I think is just a little more intuitive than in the written solutions. It may be interesting to compare my solution with the written solution. The first axiom is called the law of trichotomy, because for any two numbers a and b, exactly one of the following 3 things can happen. Either a is greater than b, a is less than b, or else a is equal to b. The first axiom is just saying that any two numbers can be compared. It says that for any two different numbers on the real number line, one is to the left and the other is to the right. The second axiom allows you to compare the relative position of 3 numbers on the real number line. It says that if a is to the left of b and b is to the left of c, then it follows that a is to the left of c. A very useful, if not terribly surprising rule. For example, you will notice this axiom being used in line 4 of the written solution to the problem of the week. The third axiom says that inequalities are similar to equalities in that if you add the same thing to both sides, then the inequality remains true. So if a is less than b, then a plus c is less than b plus c. It's called translation invariance because adding c to both a and b gives a result which is translated along the real number line by the same amount, c. In this diagram, c is positive, so the result is translated to the right of a and b. If c were negative, then a plus c and b plus c would be translated to the left of a and b. The axiom says that if a is to the left of b, then if you add c to both a and b, then a plus c is still to the left of b plus c. Here's an example with numbers. Here I've chosen a is minus 5 and b is 2. A is less than b because minus 5 is to the left of 2 on the real number line, and I let c in the axiom be equal to 10. So the axiom says that a plus c will be less than b plus c because a is less than b. And indeed, that's true, because a plus c is minus 5 plus 10, and b plus c is 2 plus 10, and yes, 5 is less than 12. So yes, it works. And the translation invariance axiom says that this will always work this way, no matter what the values of a and b and c. Combining the second and the third order axioms gives us another useful result. It allows us to add two inequalities together while maintaining the order, like this. So if a is less than or equal to c, and b is less than or equal to d, then a plus b is still less than or equal to c plus d. Take a moment to think why this property comes from a combination of translation invariance and the law of transitivity. Here's another example with numbers to see how the property works. So here I have an inequality, minus 5 is less than or equal to 3, and minus 10 is less than or equal to minus 2. And when I add the left-hand sides of this inequality, I get minus 15. And when I add the right-hand side of this inequality, I get 1. And yes, minus 15 is indeed less than or equal to 1. So the inequality is preserved. The fourth and the fifth axioms say that if you scale both sides of an inequality by the same positive number, then the inequality remains unchanged. But if you scale both sides of an inequality by the same negative number, then the inequality gets reversed. For example, let's take the inequality a is less than b. I took a as minus 5 and b is 2, and minus 5 is less than 2. And if I multiply both sides of this inequality by the same positive number p, say 10, then because a is less than b, p times a will still be less than p times b. And when we plug in the numbers, we can see that this is true, because p times a is 10 times minus 5, which is minus 50, and p times b is 10 times 2, which is 20, and yes, minus 50 is less than 20. But be careful, because if we take an inequality and multiply both sides by a negative number, then the inequality gets reversed. So if a is less than b, then if n is a negative number, then n times a is greater than n times b. In this example, with a, b, and n, I have n times a is minus 10 times minus 5, which is 50, and n times b is minus 10 times 2, which is minus 20. And yes, 50 is greater than minus 20. So we started with an inequality that points to the left, and when we multiply both sides of the inequality by this negative number, we ended up with an inequality that points to the right. And that's scale and order axiom number 2. It always works that way. And when I multiply both sides of the inequality by a positive number, the direction of the inequality remains unchanged. and that's scale and order axiom number 1. Note that if I were to multiply both sides of an inequality by 0, then the inequality is lost, because 0 times A is 0 and 0 times B is 0. So A was less than B, but 0 times A is equal to 0 times B. So the inequality becomes an equality when multiplying by 0. So we have to be careful when dealing with inequalities. You can't always treat them the same as equations. While multiplying both sides of an equation by the same number always results with equality, the same is not true of inequalities. That multiplying both sides of an inequality by a positive number, the inequality is preserved, but when multiplying both sides of an inequality by a negative number, the inequality becomes reversed, and when multiplying both sides of an inequality by 0, the inequality becomes equality. Here is one of my favorite tricks, which is a result of the scale and order axiom, and that is, if we take two positive numbers and x is greater than a, then when I take the reciprocal of each number, the inequality becomes reversed. Can you use the scale and order axiom and explain why this is true? Here is an example with numbers. So I have two positive numbers, and 10 is greater than 2. So when I take the reciprocal of each side, I get 1/10 and 1/2, and the inequality becomes reversed. And indeed, 1/10 is 0.1, which is certainly less than 1/2, which is 0.5. And this always works. To use the scale and order axiom to explain how this works, here's a hint. You take your original inequality and multiply both sides by the positive number 1/10, and then take that resulting inequality and multiply both sides by the positive number 1/2, and your final result will say that 1/10 is less than 1/2. Now that we have reviewed the order axioms, we can get back to understanding and solving the problem of the week. So we want to find all positive integers x, y, and z so that 1 over x plus 2 over y minus 3 over z equals 1. For example, here is a solution to this problem. Because if we plug x, y, z is 1, 2, 3 into this equation, the left-hand side becomes 1 plus 1 minus 1, which is 1, which equals the right-hand side. So 1, 2, 3 solves this equation, because when plugging 1, 2, 3 into the equation, the equality is true. So, yes, the triple 1, 2, 3 is a solution to this problem. On the other hand, look, I found another triple that satisfies this equation. I put x is minus 2 and y is 1, and z is 6, and that gives me minus 1/2, minus 1/2. This totals to minus 1. When added to 2, I get 1. So the triple where x is minus 2, y is 1, and z is 6 satisfies this equation. And yet, no, this is not a solution to this problem because we are being asked to find x, y, z that are positive integers that satisfy the equation. And because x is negative, I have not found a triple of all positive integers which satisfies the equation. So this triple is not a solution to this problem. It solves the equation, but it doesn't solve the problem. Because the problem specifies that we need to calculate positive integers, x, y, and z, that solves this equation. So solutions to this equation where some or all of the integers are negative will not be accepted as a solution to this problem. As another example, okay, I've found another triple x, y, z that solves this equation. I put x is 1, y is 3, and z is 4.5. And if you do the math, this sum does equal 1. And so x is 1, y is 3, and z is 4.5 satisfies this equation. But this is not a solution to the problem either, because the problem specifies that we need to find x, y, z that are positive integers. And while x, y, and z are all positive, z is 4.5, which is not an integer. So this is not an acceptable solution to the problem. And finally, as another example, so while here is a triple of positive integers, 3, 3, and 1, the result when I plug these values into this equation gives me minus 2, which is not 1, and so no, even though this triple consists of all positive integers, it does not solve the equation, so it's not a solution to the problem. Now that we understand what the problem is asking, let's start talking about how to solve the problem. The first thing I'm going to do is multiply both sides of my original equation by the product x, y, z. And I notice that this equation becomes yz plus 2xz minus 3xy equals xyz. This is an example of a Diophantine equation. Diophantine equations are polynomial equations in which only integer solutions are sought. While these equations tend to look simple enough, they also tend to be quite challenging to solve. They often require a deep understanding of advanced mathematics, including abstract algebra and number theory. Mathematicians can devote entire careers to solving just one equation like this. This particular Diophantine equation is not too hard. We can solve it using some basic inequalities, Euclid's lemma, and a little bit of factoring polynomials. Let's start by observing that we have one equation with three unknowns, x, y, and z. Usually when you want to solve a system of equations, you need the same number of equations as unknowns. But we don't have three equations here. We only have one equation. So we need more information somehow. Since we're looking for positive integer solutions x, y, and z, a reasonable approach to solving this equation could be to start plugging in some integer values for x and y, because if I knew the value of x and y, I could solve for z. So one approach to solving this problem would be to list all the possible positive integer pairs of values for x and y, and then for each of these integer pairs, compute the corresponding z values, if any, in each case. At first, this appears to be an infinite process, which will take forever to solve. But when we examine this equation more closely, we can see that many of these cases will be ruled out. Let's discuss this. So if we examine the equation that we want to solve here, and we see that 1 over x plus 2 over y is a positive quantity, and then we're subtracting a little bit, and we want the answer to be 1, well, if we take a positive quantity and then add a negative amount, and we get 1, that means that this positive quantity must be greater than 1. If we do the algebra, this equation says that 1 over x plus 2 over y equals 1 plus the positive quantity 3 over z, and 1 plus a positive quantity is strictly greater than 1. So this sum is strictly greater than 1. So we see that this part of this equation, 1 over x plus 2 over y, is a quantity which must be strictly greater than 1. So we know that if we make x and y too large, that won't happen. For example, what if we made x is 10 and y is 10? This would become 1/10 plus 2/10, which is 3/10, or 0.3, and 0.3 is not greater than 1. So that means if the x and y values in this table are too large, then this sum will not be greater than 1, and so those values won't satisfy this equation. Let's first note that there are certain values of x and y which will guarantee that this sum is greater than 1. For example, if we set x as 1, then this becomes 1 plus the positive quantity 2 over y, and 1 plus a positive quantity is certainly greater than 1, no matter what the value of y. So this whole column of values where x is equal to 1 will satisfy the condition that 1 over x plus 2 over y is greater than 1. But if x is 2, this inequality might not be greater than 1, because this is a half, and I could make this a half by setting y equal to 4, and now we have 1/2 plus a half is 1. And this is not greater than 1. It's not working. So the pair of numbers when x is 2 and y is 4 is not working. So the quantity where x is 2 and y is 4 cannot satisfy this equation, because when I plug in x is 2 and y is 4, this quantity is equal to 1. And when I subtract a little bit, there's no way that the result can still equal 1. And if we have x is 2 and y is 4 gives us 1, which is not greater than 1, certainly making the y value any greater will make this sum even less. And so we can rule out all of these values where x is 2 and y is 4 or greater, because all of these values will make this sum not greater than 1. Well, we're continuing to look for values x and y which guarantee that this sum is greater than 1. So what else could we choose? We know that when x is 1, this is guaranteed to be greater than 1. But if x is 2 or greater, then this is not guaranteed to be greater than 1. What other kinds of values could we choose to make this quantity bigger than 1? Let's look at y. What if we make y equal to 1? Then yes, because we now have 2 plus a positive amount, which is a number that's greater than 2. So it's certainly greater than 1. So this entire row, where y is equal to 1, will satisfy that 1 over x plus 2 over y is greater than 1. And also, if we make y equal to 2, then this is 1 plus a positive amount, which is certainly greater than 1. So this entire row, where y is equal to 2, will satisfy that this sum is greater than 1. But if we make y any larger, for instance, if y is 3, then we're no longer guaranteed that this inequality will work. So looking in this third column, we know y is 1 will work, y is 2 will work, but when x and y are both 3, what do we get? 1/3 plus 2/3, which is 1, which is not greater than 1. So this pair of numbers will not satisfy this inequality to make 1 over x plus 2 over y strictly greater than 1. And again, if we make the y value any bigger, that just makes this whole sum even smaller. So we can rule out all of these values in this column below the pair of integers 3 and 3, including 3 and 3. And likewise, if we make x any larger, this sum just becomes smaller, and so all of the values to the right of this pair can be ruled out, because we've made the x and the y pair too large, and 1 over x plus 2 over y will be smaller than 1, not greater than 1, which is needed. And by the same reasoning, all of the pairs in every column below this row and including this row can be ruled out because the denominators, x and y, are too large, and 1 over x plus 2 over y will not be greater than 1 for the values in this table, which I've crossed out here. So what we've established is that when x is 1, like in this column, or when y is 1, or when y is 2, as in these rows, then this inequality is true, and this sum is guaranteed to be greater than 1. But for these pairs of x and y which I've crossed out, I'm claiming that this inequality will not be true. And I can establish this formally like this. First of all, I'll establish in this column that when x is 2, the only values of y that make this sum greater than 1 are y is 1, 2, and 3, and that for all of these pairs, where the value of x and y is greater or equal to 3, then this sum will not be greater than 1. I can formally establish this first claim for this column here like this. So in this first column, when x is 2, and we know that 1 over x plus 2 over y needs to be greater than 1, for this column here, where x is 2, we can plug in 2 for x, and this inequality becomes 1/2 plus 2 over y is greater than 1. Then by translation invariance, we can subtract 1/2 from both sides of this inequality, and so this becomes 2 over y is greater than 1 minus 1/2, which is 1/2. And so 2 over y is greater than 1/2. And then by the scale and order axiom, we can multiply both sides of this inequality by the positive number 1/2, and this becomes 1 over y is greater than 1 over 4. And then by the scale and order axiom again, because both of these numbers are positive, when I take the reciprocal of each side, the inequality becomes reversed. So we have the reciprocal of this side is y, the reciprocal of this side is 4, and the inequality becomes flipped. So we have established that y must be less than 4. So we have established that for this inequality to be true, if x is 2, then y can only be one of 3 choices, 1, 2, or 3. And that answer is reflected in my table here. When x is 2, the only way for this inequality to hold is that y is 1, 2, or 3, and none of the rest of these pairs will make this inequality work. And for the rest of this table, what we're claiming is that if my x and y values are greater than or equal to 3, then this inequality cannot hold, and I can prove that formally using the order axioms like this. So what I'm claiming is that if 1 over x plus 2 over y is greater than 1 for positive integers x and y, then we cannot have both x is greater than or equal to 3 and y is greater than or equal to 3. So if this inequality holds, then x and y cannot be in this part of the table, in the lower right-hand part of this table. And the proof goes like this. Let's suppose that we know that x is greater than or equal to 3 and that y is also greater than or equal to 3. Then by the scale and order axiom, when I take the reciprocal of both sides of this inequality, the inequality becomes reversed. So if x is greater than or equal to 3, 1 over x is less than or equal to 1 over 3. And similarly for y, then another application of the scale and order axiom, I take this inequality, multiply both sides by the positive number 2, the inequality is preserved. So if 1 over y is less than or equal to 1/3, then 2 over y is less than or equal to 2/3, then, as pointed out in the previous discussion, by using the transitivity axiom and the translation invariance axiom, we can add these two inequalities together. So if 1 over x is less than or equal to 1 over 3, and 2 over y is less than or equal to 2 over 3, adding the left-hand sides of each of these inequalities gives me 1 over x plus 2 over y, and that has to be less than or equal to the sum of the right-hand sides of this inequalities, 1 over 3 plus 2 over 3. So we have established that if both x and y are greater than or equal to 3, then 1 over x plus 2 over y must be less than or equal to 1. Therefore, in order to have 1 over x plus 2 over y greater than 1, it is not possible to have both x and y greater than or equal to 3. And the claim is proved. And that's why we crossed out all of these values in the lower right-hand portion of this table where x and y were both greater than or equal to 3, because in that case, it's not possible to have that this sum is greater than 1, which is what we need in order for x and y to satisfy this equation. So looking at our table, we have found the only possible pairs of values for x and y that make this inequality true, which must be true in order for x and y to satisfy this equation. And we see that there are exactly 4 cases. So in order for this inequality to be true, we either have y is 1 in this row, y is 2 as in this row, x is 1 as in this column, and this one remaining possibility where x is 2 and y is 3. And these are the only pairs of positive integers x and y that can possibly solve this equation. So let's have a look at each of these 4 cases and let's see what happens. We'll try setting y equal to 1 in this equation and see what happens. Can we solve for the corresponding values of x and z that make this equation work? And then in case 2, we'll set y equal to 2, and then we'll try to find the corresponding positive integer values of x and z that make this equation true. And then we'll try case 3. We'll set x equal to 1 and see if we can find the corresponding positive integer values of y and z that make this equation true. And this one's going to be the easiest case, because if we set x equal to 2 and y equal to 3, we immediately have one equation with one unknown. It will be very easy to solve for z if there's a positive integer solution to that. So we've established that in order to solve this problem, we have 4 cases. Let's look at case 1 first. I'm going to plug y equals 1 into this equation and see if I can find the positive integer values x and z that satisfy this equation, like this. So for my first case, when y equals 1, I plug this into the equation that I'm trying to solve, and I get z plus 2xz minus 3x equals xz. And then I can simplify this because I have 2xz on the left and xz on the right. So subtracting xz from both sides, I have xz minus 3x plus z equals 0. Now, one way to tackle this would be I can try factoring this result like this, because I have xz, and then if I put a minus 3 on this side, I'll get minus 3x, and if I put a plus 1 over here, I'll get a plus z. I'm just getting an extra factor of minus 3 here, and that's why we have this, because this left-hand side I can see is xz minus 3x plus z minus 3. And this part is 0, so this side is equal to 0 minus 3. And so that's why this product is equal to minus 3. And then I can analyze this, because I know that x needs to be positive integer, and so x plus 1 is a positive integer. I also realize that minus 3 is a negative integer. And so in order for this product to be negative, this quantity here has to be negative, because positive times negative will give me negative. I also know that the only factors of 3 are 1 and 3, because 3 is a prime. So the only way to factor minus 3 is if this is minus 3 and this is 1, or else if this is minus 1 and this is 3, because that's the only way to factor minus 3. So that means that z minus 3 is either equal to minus 1 or else it's equal to minus 3. Now, we can't have z minus 3 equal to minus 3, because that would mean z is 0, but we're looking for positive integers that satisfy this equation. So that rules that out. So it follows that z minus 3 must equal minus 1, and if this is minus 1, it follows that x plus 1 must be 3. So we've established that z minus 3 must be minus 1, and then in this product, since this product is minus 3 and this is minus 1, x plus 1 must be 3. There's no other choice. So we've established that x plus 1 must be 3, and z minus 3 must be minus 1. We're now able to solve for x and z. So if x plus 1 is 3, it means x must be 2, and if z minus 3 is negative 1, adding 3 to both sides of this, it means z must be 2. So the conclusion is that if we start with y is equal to 1, we know that x must be 2 and z must be 2. So x, y, z is the triple 2, 1, and 2. And I'm claiming that this is a solution to the problem. And it's the only solution when y is 1. Let's check and make sure that this triple of positive integers does solve the original equation. And we can do that like this. So here we see that the triple of positive integers 2, 1, and 2 does satisfy the original equation, because if I plug in 2 for x, 1 for y, and 2 for z, we get 1/2 plus 2 minus 3/2, and is that equal to 1? Well, I'll find a common denominator, and this becomes 1 plus 4 minus 3 over 2. Is that equal to 1? And the answer is yes, because 1 plus 4 minus 3 is 5 minus 3, which is 2. So the left-hand side is 2 over 2, and yes, that does equal 1. So yes, the triple of positive integers, 2, 1, and 2, is a solution to the problem. Just as a note, when we were solving this equation and finding that the only solutions were x and z equal 2, we had to factor this polynomial in some way. And it's possible that when you looked at this, maybe this isn't the first factorization that you thought of. So there are other ways to factor this, and it will still work. But recognizing this polynomial can be factored this way with an extra minus 3 on the side was maybe the most straightforward way. But as an alternative, you could look at this polynomial this way. So you could solve for z, which is equal to 3x minus xz. Then I factored out the x, and I discovered that z is 3 minus z times x. And because z has to be positive and x is positive, it follows that this factor must also be positive. And so when I analyze that, I see that 3 minus z must be positive, which means that by translation invariance, when I add z to both sides of this inequality, I see that z must be smaller than 3. And since z is a positive integer, it follows that the only choices for z is 1 and 2. And then with a little more work, you'll rule out this. So you'll find out that z equals 1 is impossible. So the only choice that remains is z is 2. And so using this alternative would also get us the same result of x, y, z being 2, 1, and 2. So when tackling this equation, there are more than one way to try to factor and figure this problem out. If we look at it this way, this is a little more direct and a little quicker, but there are other ways to look at it as well. What we have so far is we have solved case 1, where y equals 1, and we have solved and found exactly one triple that satisfies this case, and we have checked that this triple does satisfy the equation. So in case 1, we're getting exactly one solution to the problem. For y is 1, x and z must be 2. Now we're ready to look at case 2. What happens when y is 2? Let's plug y is 2 into this equation and see if we can solve for the positive integers z and x, which satisfy this equation. So we're going to do that next, like this. So for case 2, we suppose that y is 2, we plug it into this equation, and we get 2z plus 2xz. Y is 2, so this becomes minus 6x. Y is 2, so this becomes 2xz. 2xz appears on both sides of this equation, and so we can subtract 2xz from both sides of this equation, and we get 2z minus 6x is 0. Dividing both sides of this equation by 2, we see that z minus 3x is 0. Adding 3x to both sides, we see z is 3x. And that's the answer. If y is 2, it follows that z must equal 3 times x, whatever x is. And so in the case when y is 2, we have found a solution. X, y, z must be whatever x is, and y is 2, and z must be 3 times whatever x is. And x is a positive integer, so x would be an element of this set of positive integers 1, 2, 3, 4, 5, and so on. Let's check if this does solve the original equation. So checking this result, we want to know if this is our value for x, y, and z, is it true that 1 over x plus 2 over y minus 3 over z equals 1? Well, plugging this in, we have 1 over x plus 2 over 2 minus 3 over z, which is 3x, and we want to know, is that equal to 1? And yes, it is, because 3 over 3x is just 1 over x, and 1 over x minus 1 over x is 0, and so we're left with 1 on both sides of this equation, like this. So yes, 1 equals 1. And so yes, when x, y, and z is the triple x, comma 2, comma 3x, then this satisfies the equation for any positive integer x. And we've solved case 2, where y is 2. Let's add this solution to our list. I'll just move it down just a little bit. So at this point, we have solved case 2. When y is 2, the answer is that the triple x, y, and z is x and 2 and z is 3x, where x ranges through the values of the positive integers 1, 2, 3, and so on. Therefore, these are the solutions we have so far, and that wasn't so bad. Let's try the next case where x is 1. So now we will set x equal 1 in this equation, and we need to solve for the positive integers y and z that satisfy this equation. And we can do that like this. For case 3, we're going to set x equal 1 in this equation, so this becomes yz plus 2z minus 3y equals yz. We have a yz on both sides of this equation, so we can subtract yz from both sides, and we're left with 2z minus 3y equals 0. This means that 2z equals 3y. Now 2 and 3 are prime, and if we can remember a little lemma about prime. So Euclid's lemma says that if we have a prime p that divides the product AB, where a and b are two integers, then p must divide a, or else p divides b. So here we have that 3y is equal to 2z. Since 2 divides this side of the equation, it means that 2 must divide this side of the equation. So by Euclid's lemma, that means that 2 divides 3, or else 2 divides y. Now since 3 is not divisible by 2, the only choice is that 2 must divide y. So now we've determined that y is an even number in the case when x equals 1. By the same token, We also can see that because 3 is a prime and 3 does not divide 2, it must follow that 3 divides z. So in the case when x is 1, z is a number which is divisible by 3. So if 2 divides y, it means that y is an even number. In other words, y can be expressed as 2k, where k is a positive integer, 1, 2, 3, 4, and so on. I'm going to plug y is 2k into this equation, and this will simplify for us, and we get 2z equals 3 times y, but y is 2k. And this is true for all positive integers k. And then dividing both sides of this equation by 2, we see that we have solved for z. And z is 3k, where k is any positive integer. And so in the case when x is 1, the solution of triples x, y, z is 1 for x, 2k for y, and 3k for z, where k is any positive integer. And we can check that this is a solution to the original equation, and we can check that like this. So to check this result, we'll plug these values of x, y, and z into the original equation. X is 1, y is 2k, z is 3k. And does that equal 1? And we can see that yes, that is true, because 2 over 2k is 1 over k, 3 over 3k is 1 over k, and 1 over k minus 1 over k is 0, so the left-hand side is 1, which is equal to the right side, which is 1. And so yes, this works for all positive integers k. The solution is x, y, z equaling the triple 1, 2k, 3k for all positive integers k. And we've solved case 3. Let's add this solution to our list. So we have just solved case 3 when x is 1, and we have found all the triples satisfying this equation are in this form: x is 1, y is 2k, and z is 3k, where k is any positive integer. And this leaves us with one last case to solve. It's the easiest case, because when I plug in x and y is 2 and 3 into this equation, I'm going to get one equation with only one unknown left, z. So it will be very easy to solve for z. And that goes like this. So in the final case, when x is 2 and y is 3, this equation becomes 3z and 4z and minus 3xy, but xy is 2 times 3, which is 6, so this becomes minus 18, equals, and the right-hand side, again, xy is 2 times 3, which is 6, so this is 6z, and I have 7z minus 18 is 6z. I can subtract 6z from both sides of the equation and add 18 to both sides, and the answer is that when x is 2 and y is 3, z must be 18. And this is the final positive integer triple solution to to our equation. And we can check that it works like this. So this is a new one because in case 1, y was 1 and this is 3. In case 2, y was 2. And in case 3, x was 1 and this is 2. So this is not covered by any of the previous cases. So this is a new solution, and so we need to check it. We want to know, does this satisfy this equation when we plug in x is 2, y is 3, and z is 18? And we see that this is 1/2 plus 2/3 minus this reduces to 1/6. And finding a common denominator, I have 3 plus 4 minus 1 over 6. And this indeed does equal to 1 because the numerator is 7 minus 1, which is 6. So my left-hand side is 6 over 6, which is 1. And so yes, the single point xyz is 2, 3, 18 is a solution to the equation. And we've solved our fourth and final case for this problem. And let's write that down and summarize our results. So in this final case, we have found a solution where x and y and z are 2, 3, and 18. And this gives the complete list of all of the positive integer triples which satisfy the equation 1 over x plus 2 over y minus 3 over z is 1. So reviewing this result, we have that when y is 1, x and z both have to be equal to 2. When y is 2, then it follows that z must be 3 times the x value for all positive integer values of x. When x is 1, it follows that y is an even number 2k and z is 3k for any positive integer k. And finally, for the pair xy is 2, 3, we have the solution 2, 3, 18. And this gives the complete list of all the positive integer triples that satisfy this equation. And the problem is solved.